Okay, yeah, just before I start, Brad reminded me during his talk that I promised people a volcano example, and so I put that together yesterday, and now it's on the CIG wiki. So I think Brad showed during his talk. Oh, can you hear me all right? Is there a microphone? Okay. 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 Yeah, so anyway, if you go to wiki.geodynamics.org, we have a place where we'll probably be putting more things there during the week. But anyway, right now there is the volcano example there before I forget about it. So I'm going to go through a fairly simple 2D subduction zone example. Let me, this is one that you can either follow along with and do as I'm going through it, or you can play with it during tinker time. It may be easier to pay attention while I'm doing this and then play with it more during tinker time. So this is going to go through an example of generating a finite element mesh using qubit or trellis. We're going to cover non-planar geometry. We're going to vary the mesh resolution for the problem. And we're going to show how you mark a buried edge of a fault. In 2D, it's pretty simple because it's just a point. And then we're going to include spatially variable co-seismic slip. We're going to have Maxwell viscoelastic material that we're going to run it for, I forget exactly how long, 300 years, I believe. And you can find all of the files in this directory right here, examples 2D subduction. I believe that in the interest of time, I think I'm only going to do steps 1 and 3 this morning. If we have extra time, I may go through step 2, which is just interseismic deformation. And then tomorrow, I believe Brad is going to go through the part that includes afterslip. So it's a pretty simple problem. We have just a 2D cross-section of a subduction zone. It's somewhat based on the Tohoku earthquake. So we just have continental crust over here. We have mantle material, and then we have downgoing oceanic crust. So the different steps of the problem that we'll be going through today. The first one, we're going to do just simple co-seismic slip. So this is just a purely elastic problem. We just take a slip distribution, apply it on a portion of the fault, and then look at the elastic deformation. Step 2 is purely interseismic deformation. So what that includes, it includes slip or it has 2 surfaces, actually. It has the bottom of the slab, where you have the slab moving down relative to the oceanic mantle on this side. And then on the other side, you have it moving down with respect to the continental mantle. And then you'll have a portion of the fault that's actually not slipping in between earthquakes. And then the final part is when we add to that an earthquake. So that will be step 3. And I believe, so what I think I'm going to do today are steps 1 and 3. So to do this problem, we have 2 different materials. We have the crustal material for both the ocean and the continent is going to be elastic, so there's no time-dependent deformation in there. And then for both of the mantle materials, we're going to use Maxwell viscoelastic material. And then we're going to have faults where we prescribe the slip on the fault. So we're not doing fault friction today. That will be tomorrow. So we're going to tell the faults how to slip. And then we're having fixed boundaries all around the outer edges of the domain. So the steps that we need to do to solve this problem, the first thing is you decide what geometry you need. So we've taken a 2D profile, and then to create the geometry, we'll do this within, I'm using Trellis here today. First, we're going to create a whole bunch of points. So, for instance, one set of points will define the upper surface. That'll include topography and bathymetry. We'll have separate sets of points that define the fault surfaces. And then once we define these points, we're going to connect them together into spline curves. So that's going to form the various interfaces and boundaries of our model. Once we form the curves, we're going to connect them together to form different surfaces. We'll have, you'll see as we go through it, but you'll have like that wedge of mantle material. We will connect curves together to form that surface, which is a closed surface and will be a material within our model. And we actually then end up stitching all these surfaces together, which makes it easier to operate on the geometry later on. Oh, the one thing I didn't mention also, along these curves, we're going to split the curves at certain places, and the reason we do that is for meshing later on. It's easier to have sections of the curves that we can look at separately. Once we've completely defined our geometry, then we go into the meshing portion where we define cell sizes along the various curves of the model. And then so what we do is we bias the curves so that we increase the cell size as we're moving away from the fault. And then once we've defined what our cell sizes are all throughout the domain, then we go ahead and generate our mesh. And for this problem, we're going to use triangular cells. Once we've created our mesh, then the final thing that you have to do, you have to define your boundary conditions. So we have to mark sets of nodes in our model that are going to correspond to either external or internal boundaries. Once we've marked all those, the other thing, we have to define what our material blocks are. Once we've done that, then we export the mesh, and then we can actually start running some simulations. Here is our first one. We just have a fairly simple representation of a rupture model. We're just going to do elastic deformation. And you'll see the boundary conditions here are really simple. We just have roller boundary conditions all the way around the outside of the model. Okay, step 2, which I don't think we're going to actually do today, but this is interseismic creep along the fault interfaces. So we're just essentially pushing the slab down, but we're locking it up along the part that's going to later slip co-seismically. And then the final one is when we put those two together. So we're going to have it creep for a while where the co-seismic part remains locked, and then at t equals 150 years, we're going to slip it on that co-seismic part. And then there are a lot of different things that you'll be able to do with this. And this is actually what we want you to do during tinker time. You start with the model that we already have, and then you just start playing with it and see what modifications might be something you would be interested in, or just to see what happens. You could have a depth-varying viscosity in the mantle. That's pretty easy to do. You can, let's see. Oh, okay, put viscosity in the oceanic crust. Yes, we can do that. You could have depth-varying elastic properties based on prim, something like that. You could try doing the problem with quad 4 cells rather than tri 3. This is fairly straightforward, but you would want to use a different meshing scheme within Qubit or Trellis. And then you can add multiple earthquakes rather than a single one. So you could, it's pretty easy to add multiple ruptures. And so those are just some of the things you might want to try. So the first thing we're going to do is start up this. I have to be careful because I'm connected to a licensed server, which can go away sometimes. Does that look? Boy, it's tiny on my screen. Okay, so if you're on a Mac, or I believe Windows too, the first thing you typically have to do is set the directory where you're going to be working. So there's the examples 2D subduction directory, which is where we're going to be working today. And then I'm going to open over here as the journal editor, because the way we define the different parts of the mesh is through these cubic journal files. And as you'll see, one journal file can call another. So what we end up doing is usually we'll divide out the part where it's purely the geometry. We'll have another part where we separate out the part that's purely boundary conditions. But they'll all be called from a top-level journal file, which is this mesh try3 journal. So if you look at this, you'll see the first thing it does is a geometry file. And so we'll go through the geometry file separately. Then we do a bunch of stuff where we're setting discretization size, and I'll go through that in a minute. We mesh it, we smooth the mesh, and then we have another part where we set boundary conditions. So that's a separate journal file. So what I'm going to do first, we'll look at our geometry. Okay. So also Brad had mentioned this scripting language called Afropro, which we use a fair bit, and it's nice because you can use it to define variables. You can see any variables you defined over here in this editor here. So the first thing that we're going to use it for right here is we're going to set the units to SI. This just makes it easier. We can give things in kilometers, stuff like that. So I'm just going to play the entire top part of this. Most of this is comments, but it doesn't matter if you play comments. So you'll see that as soon as I did this variable names, and so these are a bunch of unit conversions and things like that. So that happens automatically when you tell it you want to use SI units. The next thing we usually always do within our geometry file is we do a reset. And the reason for that is because a lot of times when you're meshing, you'll try several different things and say, I want to start all over. And to do that, you can just have a reset command, which clears everything you've done and starts you out fresh. So we'll do that. It won't do anything in this case because we haven't done anything yet. It doesn't reset those. If you decide you want to clear these out, you can come over here and hit delete. Yeah, it's just the way it works. Not sure why. So and this is another one, this undo off is one that in some cases I think you can overload the memory if you leave undo on. It's not going to happen for this problem, but
you'll notice that the comment there is prevent errors.
Oh, is that why it is? Yeah. It's hard to read on here. It's tiny. Okay.
And that was a bug.
That's a bug in Trellis or Qubit.
It may have been fixed since we started.
Yeah, it's an ancient bug that may have been fixed. Okay, so the first thing, this looks kind of complicated, but it's really not. We're just creating a whole bunch of vertices. This is just a set of coordinates. The first one is the topography and bathymetry. And you'll notice that a couple of them we're singling out, like this first one. We get the ID of this first vertex that we're creating, and these things here, when it starts with the hash sign and then the bracket, these are apropos commands. So what we're taking the ID of the vertex we just created and we're saving it in this variable right here. So once we do that, it'll show up down here in the apropos variables. So we do it for this one, which is our first one, is the upper west. And then we're going to do one that corresponds to where the trench is. And then we're going to do the same thing for one that's here at the east. So let me I'll just run all of those. So you'll see we've created all of these points. But what we've done over here, if we scroll up, yeah. So you'll see that now we have ID numbers for certain of the vertices. Then the next thing we're going to do is connect these together into a spline curve. And we're going to name this curve, call it topography. Okay, so there's our curve. So that's the upper part of our model. Then we're going to do something similar to define, we have the slab. We're going to do exactly the same thing. We have a rough 2D geometry that we're using. And so we just define first the vertices, and then we connect them into a spline curve. And you'll notice that, again, we're grabbing a few of the points that we're going to refer to later, and we're giving them names. It makes, rather than trying to figure out what number it is, we just give it a name, which makes it a lot easier. Okay, I'll go ahead and we'll just make the curve too. So, okay. So there, now we have the top of our slab. Okay, then we're just going to, for the bottom of the slab, we're going to cheat it, and we're just going to take this curve and just kind of move it downward in a direction more or less normal to where it goes. So what we do, we copy it and then move it to a particular coordinate. I'll just do all of that. Okay, so that's what we've done. We've ascended this one and kind of just moved it down. And we're going to make another spline curve through those points. Okay, so now we have, this is really, you know, the basics of our model here. We have the top, we have the slab. Now really, okay, we have to put in the crust mantle boundary. So we're going to create a vertex at a particular coordinate, 40 kilometers depth. We're going to name that vertex. And we're going to, we've already named one that's the moho there. So what we're going to do is create a spline through those two points. Okay, so we just made a spline through that point, and it's just a constant depth boundary. Okay. Let's see. Then, okay. Let's see what we've got so far. Okay, yeah. So now all we have to do are the outer parts of it. So we're going to take, like this is going to be the corner here. We'll draw spline curves essentially that just go around the edges of our entire domain. So we just have to make a few more vertices first, and then we draw the spline curves and connect those together. Okay, so we're not done yet because first of all, we don't have any surfaces in our model yet. And we need to also do some splitting of the curves, and that's for when we do the meshing later on, and for applying boundary conditions. So the first thing we're going to do is our topobathy curve where it crosses the slab top curve. So let's see, So we're going to split this curve right at this point here. Okay, now where we had one curve, now we have two separate curves. And we're going to do our other curves. We're going to split the slab top where it crosses the continental moho. We're going to split our western boundary where it crosses the continental moho. We're going to split the bottom where it crosses the bottom of the slab. And finally, we're going to split the eastern part where it intersects the bottom of the slab. So and we'll have all of our split curves. Okay, so now we have all those separate curves. Okay, the next thing we have to do is we have to make surfaces that correspond by curves. So to do that, for instance, the first thing we'll do is the continental crust up here. So you can see it's bounded by 4 curves there, and here we have them named. So there's the topobathy curve, the edge west. Actually, what I probably should show you is you can have trellis or trellis cubit select different things depending on what you've selected here. And so here I've told it to select curves. So if I click on something here, it'll tell me what curve that is. It'll give it the name and the number corresponding to that curve. So we can see which ones are surrounding here. You can also see them up here. There's all of our 3 curves. And so we're going to connect this first batch together to form a surface. And then we're going to give it a name. Okay, so we made this surface that's bounded by those 4 curves. Then we're going to do the same thing with all of our other surfaces that we want. We're going to connect these curves to get our to get the continental mantle. We'll connect all of the ones surrounding the slab, and then we'll do the same thing for the oceanic mantle. So I'll just go ahead and do those. Okay, so there we have all of our different surfaces, and you'll see that now we have some sheet bodies, which are, there's our continental crust. We've named them all. Have our continental mantle, oceanic crust, and then our oceanic mantle. So that's the surfaces we're going to need for our model. Then we don't need these vertices anymore because we've already made the curves. So we're going to do that as vertices. Then the next thing you have to do, well, actually, for this, we don't have to do it for this 2D example. We don't have to imprint and merge because we don't have any coincident surfaces.
Yes, we do.
Do we? No, they're single surfaces.
They're single surfaces, but I'm not sure if the curve, if it knows that the curves are exactly the same.
I think, well, let's see. Yeah, well, it'll tell us what it does. So, it did merge some curves. Yep, okay. Okay, so what that does, the first thing you do is imprinting. That failed, yeah. Imprinting happens, that surfaces. So an imprint lets Trellis know where one surface is coincident with another surface. And then merging is actually when you merge together coincident surfaces. So typically you have to do both of those steps. Now in this 2D model that turned out not to be the case, but we've merged together all of the curves that were coincident. Then the next thing we have to do, this is to make additional steps simpler, we do something called stitching, which is where we take all of the surfaces that were created and merge them together into a single, we're calling it a volume, but it's really just a surface. And so you'll see what happens when we do that. Boom. Now it's a single sheet body, but it is composed of all these separate parts. So it's really just a convenience thing. Okay, let's see. Okay, then we're going to split the top of the slab. Okay. So that is going to be, that's going to be for our co-seismic slip, I believe.
So you had a question about how to describe parts of the fault that you want. So that's where we come in and we split curves that are longer than what you want. Yeah. Like a piece of a fault. In this case, it's
so now what we've done, we've split, this was one curve, and now we've split it into two. So this is going to be our co-seismic fault slip. Okay. Then, then we're going to split this similarly. So we'll split that into two curves. Okay, so now we've split this curve right there. Okay, and then then we're going to do the same thing for the bottom of the slab. So now we're going to split this curve. Okay, so now, yeah, we have 3 pieces of the slab bottom there. And so that, now that we've done this, completely defined the geometry that we're going to need for both meshing and to apply our boundary conditions. So part of the things we're doing are not maybe entirely obvious when you're creating the geometry, but once you start doing the meshing and the boundary conditions, you can understand why we split certain curves at certain places. So I'll go ahead and or should I see if there's any questions about the geometry before I Okay, well, the imprint lets the surfaces know where they're coincident, so they're aware of each other. But the merging actually merges them together.
Well, so that say you have 2 volumes and you split one volume in half, but you don't split the other volume in half. So where they meet, there's an intersection on one side and not on the other. The imprint lets this volume know that that intersection came in, and so then it'll split the corresponding curve on the other side. But Qubit will keep 2 separate curves even where surfaces meet. And so the merge then merge those curves in common where they're coincident together.
Yeah. They have them as separate steps because in some cases you may actually want to, not any that we have in Pilot, because for instance, like a fault, we split it ourselves. We don't have the meshing software do it. So I guess that could probably happen. You mean that like, for instance, 3 surfaces that are, yeah, that, and then you definitely want to merge because you don't want. No. If you do, when you do merge all, it will put all of the, it does vertices, curves, and surfaces. It'll merge all of those together. There's some things that happen in 3D that do not happen in 2D, and I think we'll go through that in, yes. Oh, I had to do it. If you notice, all of these things up here have little things you can grab them. You can grab it, and I grabbed it because it was annoying me where it was. I grabbed it and put it down over here. Yeah. Okay. So this is our main journal file. And so you'll see that the first thing we do this journal file is called the geometry journal file. So we've just done the geometry. So the next part we're going to do has to do with meshing. So first of all, what we're going to do is tell it we want to use triangles to mesh this this surface. And we start out this scheme that these 2 commands have to do with the sizing. And so we're going to start out by saying it's all undefined. We don't want any defined sizing function because we're going to do all of that ourselves. So we do that both for the curves and for the surfaces. So first of all, we'll just do this. And that will set our meshing scheme. So it doesn't actually do anything there, but it does affect what the meshing will do. So the next thing we're going to do, here again we're using apropos. We're defining dx. That's going to be the size along the, I believe the cosize, I think that's on the coseismic part of the fault. And then we're also going to use bias sizing function. If you look in the qubit manual, it has a lot of different types of sizing functions, but this is one where it's just a geometric rate of increase of the mesh size with distance. And so we can give it a bias factor. That's how much it increases for each increment that you move along the curve in this case. So we're setting dx to 8 kilometers. We're setting a bias factor of 1.2. And then we're going to say curve slab top at A, slab top at D have size of dx. So we can see which parts that are. Those are. We come up here. Let's look at the. You
can also use the locate command.
Yeah. Okay. Yeah. Okay. I can do that. Locate. Which ones are we looking for? Slab top at.
You do curve.
Yeah. At A? Okay. So you can do it that way. I usually like to just click and see what they are. So there's that one. I believe those were the two. Yeah, so what we're going to do for those two, we're going to give it a constant mesh size of 8 kilometers. And we're also going to do the same topobathy, which is that part right there. So let's see. Okay, I didn't play that part yet, did I? Do that, which won't do anything except that it will give you some new variables over in your apropos variables there. And then we're actually going to set the discretization size. So if we look, we can do so what that'll do is shows what we've done so far. So right now, all of these have default values, but right here and here, we've set this discretization size to be much finer. So now we're going to continue through the rest of the mesh and set these discretization size. Some of them will be constant, like we've done here, and some of them are going to have a variation so that they'll get coarser as you move away from the fault. Okay, so now we're going to use the bias sizing function on several of these. Topobathy at B, we're going to give it a fine size, which is the 8 kilometers. We're going to give it bias factor, which is 1.2. We're going to tell it which vertex to start. So topobathy at B is this curve here. We want to look at it. Let's see if we look at continental mantle. Oh wait, no, continental crust, sorry. This one. So we want to know where to start. So vertex 75 is this one closest in. So that's where we're going to start. And then we're going to coarsen it as we move outward from there. So that's what that command is doing. So we're telling it define size, bias factor, and then where to start. And we're going to do that actually for quite a few of these. It's basically the same idea. And some of them we're going to have maybe a finer, fine size, but yeah. So I'll go ahead and do all of those bias vectors. Now, if I can look again, now you'll see what we've done. We've got it so that now it coarsens out with distance along here. Same way here, and there. And then we're going to set, I think the outer ones we're going to just set to a constant size of 50 kilometers out along the edges of the mesh. Okay. So we've done that. Now we've defined all of our sizes so we can go ahead and generate the mesh. We've already told it we're going to do a triangular mesh, so once we do that, there we go. So I can just yeah, so there's our mesh, and you'll see what we've done. We've got the finest size in here where there's going to be the most going on along the fault, and then we coarsen it as we move away. So that's a lot of what we have to do. Now, once you've created a mesh, frequently the quality isn't as good as you would like. You might get skinny triangles. In 3D, you can get slivers and things like that. So what you're typically going to do is improve the quality of the mesh. You can tell what the quality of your mesh is by using these nifty tools over on the side. There's the little badge that shows its quality. We're going to have it look at all of the surfaces. And usually the metric that we use is condition number. That's kind of a nice one. We'll have it display a graphical summary for us, and then we'll just have it do that. So you can see here we have condition numbers that go up as high as 2.65. In general, you want your condition number to always be less than 2, and the lower you can get it, the better off you are. So what we're going to do is go through just one round of smoothing for this mesh and see if we can improve it. So we're going to have it smooth all surfaces. It has a lot of different smoothing schemes. You would have to look in the manual to see what they all are, but condition number is a good scheme. Beta is the what you want your maximum condition number to be, and then CPU 10 just tells you how many minutes you're willing to allow it to do this. And then we'll once we've defined the scheme, then we'll smooth it. So we'll go ahead and do that. Okay. That was pretty fast. So let's see if that improved things. Oh, it didn't really.
No. Well, you can see that
it's
the top
just
corner, it's the corners.
Yeah, those are not. Yeah.
Where the geometry is sort of, and we set the discretization class to be sort of baked for the geometry. That's why it created squished cells.
So this is, you can't just assume that it can do it for you. You might look at this and say, I see where it's being messed up. So you could have a bias factor that's not quite as high. And also you would set maybe the resolution out here to be a bit finer resolution than what we told it. So we're going to go with what we have here because I think it'll still run just fine. But in general, you want to try and reduce that as much as you can. So now we've done that. The final thing is to set up your boundary conditions, because right now you have a mesh, but PyLith has no way of knowing which materials correspond to which cells, or which sets of nodes correspond to which boundaries. And so we have to tell it. So what we do, we have the separate create BC journal file. Okay. So the first thing we're going to do is define material blocks. Different materials. We'll have the continental crust, continental mantle, oceanic crust, and oceanic mantle. And so what we're going to do, we have our different surfaces here. So we have, there's our continental crust. We're going to assign that to a material block. So to do that, block 1 consists of surface continental crust. And then we're going to give that block the name continental crust. Similarly for our continental mantle and those four. So just do that. So there we have that. And if you come up here and look at your blocks, now these are our material blocks. There's continental crust, continental mantle. So those are our materials. So that will let these ID numbers here, these are important because we need those ID numbers in our PyLith configuration file so it knows what ID number to associate with each material. Then, in a somewhat similar way, now we have to define node sets. So first thing, node sets are just sets of nodes that correspond to surfaces. Or they don't have to correspond to surfaces, but typically they do. And so to create a node set, we do it in 2 steps. First, we usually create a group. A group is something that's only internal to qubit or trellis. But the handy thing about groups is you can do all sorts of logical operations on them. You can intersect groups. You can unite them. You can operate on them by coordinate like that. We don't have to do that in this case. But typically, you do want to have a group first. And once you have the group that defines the set of nodes you want, then you assign that group to a node set. So the first one we're going to do is the coseismic part of the fault. So we're first going to add a node in slab top at A. So we come up here. Oh, let's see. I want it to be that. So that's slab top at A. There's slab top at D. So we're going to add those 2 node sets to the group called fault coseismic. We'll first do that. Okay, so now if we come over here to our groups, we have this one called fault coseismic, and it's just the nodes that are on those 2 curves. Now that we have the group that does what we want, then we'll say, okay, let's make that a node set. And these numbers are somewhat arbitrary, but I believe that we typically start them values 10 and higher. So here we're giving it, but they do have to be unique. So we're calling this, we're going to give, first we tell the node set 20 that it's going to consist of fault coseismic, and then we give that node set the same name. So we'll do that. So there we go. So that was our, but now we also have a node set. So I can undo there, but now we see that that's our node set now. So then we just kind of go through and mark all of our boundaries that way. Now the one thing here, Brad mentioned that in PyLith 2.0, we now, if your fault ends internally, then you need to mark the edge of the fault. So in 2D, that's easy. It's just it's a point where it ends. We're going to do that here, although I don't believe we actually use this information in our example problem, but this is to show you how you would do it if you wanted a fault that ends inside of the volume. So we just say fault coseismic edge, add node in vertex 74. So it's just a single vertex. So you can, if we look at there's vertex 74. So that's our fault edge right there. So we're just going to mark that one so that PyLith will have that information available. Okay, so now we have fault coseismic and the fault coseismic edge. Now, this is pretty much the same sort of thing. We just take these curves that correspond to different parts of our model and we add them to a group that we want. Once we have them all in the group, then we make a node set out of that group and give it a name. So I'm going to do that for the slab top and the slab bottom. All right. Okay. What time am I supposed to finish? Really?
We started half an hour. We go to 11.
Yeah. Okay. All right. So anyway, there's our node set, slab top, slab bottom, and I am going to just flip through the last ones, which are just the outer boundaries. I think they are. Let's see. Yeah. That's our outer boundary. So.
Can you say why you removed that node?
Ah. Okay. Let's see. Let's go back and see what I did. 4. Yes. Okay. So this one here, I removed. So if we look at this node set for the boundary east mantle. Yeah, let me, yeah. Yeah. So if we look here, what I've done, I've removed this node that was right here. The reason I did that is because we're going to want to apply boundary conditions along here. And this is going to be a fault. And one thing that we can't do, we can't apply boundary conditions to a fault node because it's got its own stuff that it needs to do. So that in cases where we have an intersection of a fault with an external boundary, we typically remove the fault node from the external boundary, or in some cases it may make more sense to remove that particular fault node from the fault node set rather than from the external boundary node set. Yes, that's true. You could apply a Neumann boundary condition. That's true.
And we won't this way you can do it. So
okay, that's good to know. Okay, so now essentially we've done everything. The last thing we have to do is just export the mesh, and then we'll have this Exodus file here. So we just did that, so I won't play that back. We just did. And now we exported it. So we had 1331 elements, 712